Well, thank you very much. That was a pleasant surprise. I've got a lot to live up to now. Okay, so my name is Vince Vu, and I'm going to talk today about some work we've been doing on looking at the theoretical properties of sparse PCA and high-dimensional data analysis. So I want to start with a caricature of a problem that I face as a statistician quite often, which is that suppose I have a data set consisting of IID observations on p variables. So x1 through xn are IID. I have n observations. Each of those is a p-dimensional vector. Okay, so the problems I typically face involve problems where p is large and n is small. And so since p is so large, I want to do some dimension reduction. One natural way to do that, very popular way to do it, is with principal components analysis, or PCA. So the idea behind PCA, this is a two-dimensional version, is that I have my data points and suppose that they lie in this cloud here. What we suspect is that the points lay close to some lower dimensional subspace, so in this case a line, given by this blue line here. And so we don't lose too much information by projecting the data points onto that line. Okay, so this is the idea behind PCA, at least when p is equal to 2. When p is bigger than 2, it's a little harder to visualize. So it turns out that this type of problem of finding this blue line is related to the problem of estimating the eigenvectors of a population covariance matrix. So I imagine that my data are actually drawn from some unknown underlying population with some covariance matrix given by sigma. And what I need to do is I need to estimate the leading eigenvectors of this covariance matrix. So some natural questions I might have are, since I'm doing estimation, how many samples do I need to accurately estimate these eigenvectors? So classical theory gives us an answer, which is, it's been known for about 60, 70 years now. If my dimension is fixed, p is fixed, but I let my sample size increase to infinity, then my accuracy is going to go down like 1 over the square root of n. Okay, so as long as I don't have too many variables and have a lot of samples, then I can accurately estimate the eigenvectors. Now the question is, what if my p is 10,000 and n is only 1,000? Okay, so does classical theory apply in this case? I don't think so. I think that what classical theory says about this situation is not appropriate. The asymptotics are not appropriate for this situation. Okay, so a typical example of this case where I have tens of thousands of variables and just 1,000 observations is one that I encounter in my applications of neuroimaging data analysis. So this is just some examples of structural MRI. And what I do is I work with psychologists and neuroscientists, and we looked at functional MRI data. And typically the situations we face there involve 10,000 plus variables and just a few thousand, or maybe just 1,000 observations, so 1,000 images. Okay, so what our paper does is it looks at PCA when p is on the order of n, so I have just as many variables as samples are. Possibly the number of variables is much greater than the sample size. And what we want to do is we want to look at a case where if we suppose a leading eigenvector is sparse, how well can we actually estimate it? So our work answers the following questions. How well can I estimate the leading eigenvector? What's the optimal error rate? What's the best I can do? What procedure attains this optimal rate? And so L1 penalization, L1 constraints are very popular. Is there a theoretical justification for using L1 constrained PCA? All right, so the plan for the rest of the talk involves 3 sections. So in the first section, I'm going to talk about going from classic PCA to sparse PCA. In the second part, I'll talk about what the Minimax framework does and why it's useful to look at Minimax error rates. And then finally, I'll present our results. I'm not going to go into the proofs at all. If you're interested in them, they're in the appendix to the paper. Okay, so classic PCA is what I refer to as just the ordinary PCA that most people learn about in Stat 101 or maybe 102. And this is PCA based on the sample covariance matrix S sub n. So I have my observations x1 through x sub n, and I form this cross product matrix, average it over the observations, and that's my sample covariance matrix. Sometimes it's called the empirical covariance matrix. So the problems of this is that it's been known that the leading eigenvectors of the sample covariance matrix are actually very poor estimators of the population covariance matrices eigenvectors. Okay, so the first rigorous proof of this appeared in the early 2000s and had been observed earlier in the 1990s by physicists. Another problem with classic PCA is that these eigenvectors that I get, the sample eigenvectors, they typically load on all the variables. So if I have an estimate of the first eigenvector, let's call it theta hat, the entries of theta hat will all be non-zero typically. Okay, so it can be very difficult to interpret if I want to go back to my original variables. So generally, in high-dimensional data analysis, doing estimation in high dimensions, It's generally a very hard problem because we have just unconstrained parameter space. Okay? So what you need to do is you need to have additional structural constraints on the parameter that you're trying to estimate in order to hopefully have a good estimate. Okay, so structural constraints can lead to feasible estimation. So a natural question that people have been asking now is, well, what sort of structural constraints make sense? And the one that has gotten a lot of attention over the past 10, 15 years is the idea of sparsity. Okay, so qualitatively, sparsity just says a few of the variables have large effects, most of the others are negligible. So sparsity in itself it seems like a nice idea, but it's really appropriate after a sparsifying transformation. So sparsity might not apply to the variables as I've collected them. And what I want to do is I want to transform them in such a way such that the representation of my data has a sparse, or after the transformation, my data, or the signal that I'm interested in, actually has a sparse representation. Okay, so examples of transformations that are sparsifying are things like basis transformations, so wavelet transformations, Fourier transforms, etc. Okay, and so sparsity can make estimation feasible, and it can certainly help interpretation. So going back to my example with neuroimaging data, so here's a caricature. These are my slices of the brain, and it's typically known that in functional MRI, when you're looking at task-related activity in the brain, it tends to be spatially localized. So there are a few regions in the brain that are actually active during a given task. The problem is that often the locations of the activity are not known in advance, but the assumption is that only a few of them are active. Okay, so in this case, sparsity corresponds to actual spatial localization in the brain images. Okay, so sparse PCA uses this idea of sparsity and marries it together with PCA. Okay, so there have been a lot of methods that have been proposed. The earliest, I think, appeared in the early 2000s by Ian Jolliffe, and many more have been proposed thereafter. Most of these methods have very few theoretical guarantees on their accuracy, so on their statistical error. And some of the prior results on theoretical results require very strong assumptions on the covariance matrix. Okay, and so if you're familiar with this literature, this assumption is called the spiked covariance model. And previously, consistency of L1 constrained sparse PCA was not known. Okay, so the framework that we're going to use to look at the sparse PCA problem is the framework of the high-dimensional Minimax. Okay, so statistical Minimax theory is concerned with what is the best possible error rate. And what Minimax does is it wants to find the minimal error in the maximum, well, best possible error in the worst case. Okay, so the min is the best and the max is over the worst. Now the use of Minimax theory is that we typically want to understand how the Minimax rate relates to other features or parameters of the problem. So specifically, we want to look at how the structural constraints, so in my case, sparsity, affects the difficulty of estimation. And hopefully, what we can do is we can pin down what the Minimax rate is, what is the best possible rate, and then look at computationally tractable procedures and see if they actually attain the optimal rate. So to apply the Minimax framework, there are a few ingredients that we need. Okay, so the first ingredient is a loss function. This is the thing that measures how far my estimate is from the truth. Okay? The second ingredient is the parameter space. This sort of embodies the idea of structural constraints. So the truth belongs to some subset. And the third ingredient involves the scaling of the parameters. And so in our work, we look at high-dimensional scaling. So we're specifically interested in how does the Minimax risk scale as a number of variables varies, number of samples varies, and the sparsity level varies. Okay? So for sparse PCA, we looked at estimating just the first eigenvector. And the loss function that we use is the Frobenius distance between the one-dimensional projectors. So this is kind of hard to understand just by looking at this equation, but I think this is the right loss function when you're thinking about dimension reduction. And in the case of just a single eigenvector, it reduces to the sign of the angle between the vectors, okay? For the second ingredient, we assume that the leading eigenvector is actually sparse. So from now on, theta 1 is the leading eigenvector of the population covariance matrix. And we're going to assume that theta 1 belongs to some L cue ball. Okay, so the easiest case is Q equals 0, L0 ball. So if theta 1 belongs to an L0 ball, it means that it has exactly R0 non-zero entries in it. Okay, so R0 is going to appear a lot, and that's just the number of non-zero entries in my eigenvector, the number of active variables. In the other cases for LQ, for Q larger than 0 but smaller than 1, those cases refer to what we call as soft sparsity. So not exactly some number of non-zeros, but many of the coefficients will be close to 0. And different Q's just correspond to different decay rates on those entries of the eigenvector. Okay, so on to our results. So before I can discuss the results, I have to introduce just a little bit more notation. Okay, so the first one is that I'm going to assume, well, this is just really just a definition, which is that the population covariance matrix sigma has a spectral decomposition. Theta 1 is the first eigenvector, lambda 1 the first eigenvalue, lambda 2 the second eigenvalue, and so on. We assume that the leading eigenvector, theta 1, belongs to an LQ ball of radius RQ. So we're really, in my presentation today, I'll focus on the case Q equals 0. The third definition, the third thing that we need, is the effective noise level. Okay, so this effective noise level, I'll explain more of it in a couple slides, but it relates to the gap between the first and the second eigenvalue. So the idea is that when these eigenvalues are close, it's very hard to tell the first eigenvector from the second eigenvector, and so your effective noise will be large. When the gap is large, the effective noise is small. Okay, so our first result is a lower bound on the minimax error. And the assumptions that we have to make include the following. So the first assumption is that we assume the data are IID. So x1 through xn are IID. And moreover, they're drawn from a distribution of sub-Gaussian tails. And so what that means is if I look at any one-dimensional projection of my observations, the tail probabilities decay like a Gaussian at worst. Okay, and the other assumption is that theta 1 is the first eigenvector. It actually belongs to an LQ ball. And we have some regularity conditions on P, N, and RQ. But those are a little hairy, difficult to explain, so look at the paper. All right, so under these assumptions, we've been able to show that if you have any estimate of theta 1, which I'm calling theta hat 1, it has to obey this error bound. Okay, on the left-hand side is the error of the estimator. On the right-hand side is this somewhat complex quantity. Okay, so let's look at this quantity here. It's easiest to understand in the Q equals 0 case. So here, Q equals 0 and R0 is the number of active variables. These are the number of non-zeros in my eigenvectors. Okay, so on the left-hand side is the error of any estimator. On the right-hand side is the lower bound. So the first term, which is the min in that 1, the reason it's there is because the error can never exceed 1. Okay? So this is simply because the sinusoid is bounded between -1 and 1. The second term, which is in red, maybe you can see that, this is the error that you would have if you actually knew the active subset of variables. If I knew which R0 variables were involved, I would just do PCA on that subset of variables. And then this is the error I would have. Okay? But the fact is that we often don't know which subset is active, and so we have to pay a price for searching. And that's what this third term is, this log term. Okay, so this log term, this is the error that's actually that you get due to variable selection. So another useful way of looking at this lower bound is in terms of the effective sample size. So what you can do is you compare this, the quantity on the right, to the classical error rate. And by doing this comparison, you can see that this is saying that the effective sample size is not actually n, but it's n divided by R0 log of the number of variables. Okay, so the bottom line is that the effective sample size is not n, but it depends on the dimension of your problem and the underlying sparsity. Okay, so if you have a less sparse problem, then your effective sample size is smaller. If the truth is more sparse, then you have a larger effective sample size. Okay, so now let me go back to talking about this effective noise variance term. So I defined this effective noise variance, or noise level term, sigma squared. It depends on the first and second eigenvalues. The reason I define it this way is it's actually pretty interesting. So about 3 years ago, there was some work on minimax rates for sparse regression. And it turns out that if you define the effective noise level in this way, our lower bound actually matches the lower bound that you get for sparse regression. Okay, and so what this is saying is that the sparse PCA problem is somehow statistically just as hard as a sparse regression problem. Okay, so that's the lower bound. And for the upper bound, what we do is we actually construct an estimator and show that it achieves the lower bound's error rate. Okay, so the estimator that we use for the upper bound is the LQ Sparse PCA Estimator. Now, this estimator is mostly useful for theoretical analysis. I would not recommend that you actually use it in practice. Okay, and so what this estimator does is it is a constrained variance maximization problem. So basically, without this term here, without this LQ constraint, this would just be your usual ordinary PCA problem. But what the LQ constrained sparse PCA estimator does is it adds an additional LQ constraint on your estimate. Okay? So the case Q equals 1, this is what is sometimes referred to as lasso. This is the one that has been proposed previously. All right, so in general, this optimization problem is actually very hard. It's a convex maximization problem. It's not a minimization problem. It's a maximization problem. So what that means is that there are potentially multiple local maxima. And so it can be very difficult to find a global maximum. But the analysis of this procedure is actually not too bad. Okay, so for our upper bound, what we do is we have the same assumptions that we do for the lower bound. But we also assume that you know what regularization parameter to choose. Okay, so in practice, you wouldn't actually know how to do this, but for theoretical analysis, it makes sense. So what we're able to show is that if you know the correct regularization parameter to choose, and in the case Q equals 0 or Q equals 1, then the LQ sparse PCA estimator satisfies this upper bound here. Okay? And so if we compare this upper bound, so this is the upper bound for the case Q equals 0 or Q equals 1 with the lower bound, which I showed previously, then what you see is that the lower and upper bounds match in terms of P, the number of variables, and the sample size, and RQ, which is basically the sparsity level. Okay? The only difference is that the effective noise level is different between the upper and lower bounds. So I think that the mismatch there is just an artifact of our analysis. Okay, so there are a couple of other consequences of this upper bound. So the first consequence is that in the case Q equals 1, this shows that the L1 constrained sparse PCA is consistent. Okay? And so in particular, it's optimal if your true eigenvector belongs to an L1 ball. We have analogous results for Q between 0 and 1, and those are in the paper. And finally, as I said before, the matching upper and lower bounds and the fact that it coincides with the rates for sparse regression say that statistically, the difficulty of sparse PCA is the same as the difficulty of sparse regression. Okay, so this is the end of my talk. And what I've hoped to show you is that in high dimensions, PCA is nearly impossible without structural constraints. But it can be possible if you employ sparsity constraints. So it's useful to think about sparse representations before applying PCA. So think about transforming your variables into some basis where there is a sparse representation of the signal you think might be there before applying PCA. So in the sparse case, the effective sample size is not n, but it depends on the dimensionality of your problem P and also the underlying sparsity level. So if you have under a signal that is truly sparse, then you have a larger effective sample size. There are some open problems that are left by our paper. So the first one is that LQ sparse PCA procedure, you wouldn't actually be able to compute it. Okay, so the optimization problem is hard, even when Q equals 1. So a challenge that is open is that are there computationally tractable procedures that actually attain the optimal rate? Okay, and that's it. So thank you, everyone.
Time for questions. Formulate the loss function in terms of a projector, so projecting onto the principal eigenvector.
Yeah.
Definitely, that's sort of projecting onto the eigenspace spanned by more than one the principal component. Is that straightforward?
So we've been working on extending this work to estimating the first D eigenvectors. So in that case, there are some tricky issues, in particular if you have multiplicity of eigenvalues, and these eigenvectors aren't necessarily unique. And so what we're looking at now is the problem of estimating the principal subspace, so the subspace spanned by the leading D eigenvectors. And we're pretty close to getting optimal rates for that.
Any other questions?
So for the subject reality assumption, do you think it can be relaxed just for non-exponential fields, or do you really need such an estimate?
So that assumption comes in when you apply, so in the upper bound, we use some really advanced results from empirical process theory to basically control the difference in the empirical loss function, the Oracle loss function. So without the sub-Gaussian assumption, I believe that you would get a larger term for the variable selection part. So that log of p would be something else.
Any other question? Otherwise, let's thank the speaker.
Thank you.